The geometric series formula states that if we sum from k equals 0 to infinity, z to the k, it equals 1 over 1 minus z, provided the modulus of z is less than 1. The series diverges if the modulus of z is greater than or equal to 1. Now we can view this from the perspective of power series by stating f of z equals 1 over 1 minus z has a power series expansion centered at the origin whose disk of convergence is the unit disk. So what we're going to do is we're going to use some algebra magic and combine the geometric series formula and expand other functions as series centered at the origin and elsewhere. So for example, let's take the function 1 over 3 plus z squared and try to expand it as a power series centered at the origin. The idea is that we want to get something of the form 1 over 1 minus something to which we can apply this formula. So what I've done in the denominator, I factored out a 3, and I wrote change this positive sign to minus a minus sign. So this is the same as 1/3 times 1 over 1 minus parenthesis minus z squared over 3. So just a little bit of algebra. You might want to pause and check that this is true. So if I look at this and I compare it to that, I can see that the common ratio, which is z up here, corresponds to minus z squared over 3 down there. So I'm going to take minus z squared over 3 and I'm going to substitute it in for z right there, and here's what I get. Now we're going to simplify this a little bit. Minus z squared to the kth power is minus 1 to the k times z to the 2k over 3 to the k. And then we're going to bump this third in, so we now have minus 1 to the k times z to the 2k over 3k plus 1, where k is summed from 0 to infinity. This is a power series expansion for 1 over 3 plus z squared centered at the origin. And this is valid provided that our common ratio, minus z squared over 3, has a modulus of z less than 1. So in other words, if we manipulate this a little bit, the modulus of z squared is less than 3, or the modulus of z itself is less than root 3. So this function has a power series expansion centered at the origin whose disk of convergence is root 3, modulus of z less than root 3. Okay, now we can expand upon this idea for a rational function whose numerator is also a polynomial in z. So let's say we look at f of z equals z plus 1 over 3 plus z squared. So we could break this up as z over 3 plus z squared plus 1 over 3 plus z squared. We already expanded this as a power series centered at the origin. Here is our formula. We could factor a z out of this. We'd have 1 over 3 plus z squared, and we could replace 1 over 3 plus z squared with our power series expansion again from above. And so what we would get is the following, because I could multiply z times z to the 2k to get z to the 2k plus 1. Of course, it would be nice if we can combine this into a single power series expansion, but that's going to become more of a headache, and it's not really worth it. So the important thing is that now we have a power series expansion, not just for 1 over 3 plus z squared, plus z plus 1 over 3 plus z squared. Because the disk of convergence of this was modulus of z less than root 3, and the same thing for this, the disk of convergence is modulus of z less than root 3 for the two series combined. Now suppose f of z is z to the 4th plus 3z squared plus z plus 1 over 3 plus z squared. We want to expand it as a power series centered at the origin. Well, the degree of the numerator is greater than the degree of the denominator here. So what we could do is perform some log division. I'm not going to go through the details of that. You could do it by hand or using Wolfram Alpha or various tools. But if we take this and divide it by 3 plus z squared, we get a quotient of z squared plus this is our remainder. Now, z squared in itself is a power series expansion centered at the origin consisting of one term. So we simply take our z squared and add the power series centered at the origin for our previous result, which is what we get right here. Now suppose we wish to expand the function f about a point which is not necessarily the origin. Now we can perform similar algebra magic in tandem with use the geometric series formula to make this work. So let's suppose that f of z is 1 over z, and we want to expand it as a power series centered at 3, not at 0. So what we're going to do is we're going to expand. We want to expand in terms of powers of z minus 3. So I'm going to take 1 over z, and I'm going to write it as 1 over 3 plus z minus 3. Now you can kind of see where I'm going. I'm kind of moving towards that end result formula for the geometric series. I want to somehow get 1 over 1 minus something. So let's make it look that way. Well, the first thing I'll do is I'll factor a 3 out of the denominator. And then I'll have 1 minus the quantity z minus 3 over 3. So now I can apply the geometric series formula to this, where my r value, my common ratio, is going to be just that quantity there. If I do that, I get the 1/3 is out in front, the series from 0 to infinity, minus the quantity z minus 3 over 3 to the kth power. I can simplify this a little bit. This is minus 1 to the k power times z minus 3 to the k power over 3 to the k. And then finally, I could multiply back by this 3. And so I get a nice series expansion for 1 over z about z naught equals 3. Now, this is going to be valid if my common ratio, which was minus the quantity z minus 3 over 3, is less than 1 in modulus. Well, if we play around with this, this is the same as saying the modulus of z minus 3 is less than 3. So that's the disk of convergence. Let's do a power series expansion for the same function, however, now centered at z naught equals I. So we're really going to be doing the same thing, except instead of having z minus 3, we're going to have z minus I instead. So I'm going to factor an I out of the denominator. It looks a little bit foreboding, but there's what I get. So now I have, if I want to pause and just check this, if I factor an I out, I get 1 over 1 minus the quantity minus z minus I over I. So now we have something of the form 1 over 1 minus something. We could apply the geometric series formula to that. I have 1 over I out in front. I have minus the quantity z minus I over I to the kth power. We're going to simplify that a little bit. We would have minus 1 to the k. We'd have z minus I to the k. We'd have I times I to the k, which is I to the k plus 1. But of course, dividing by I is the same as multiplying by negative I, so we would get the following. So here's a series expansion, power series expansion, centered at I for the function 1 over z. Now the series expansion is valid provided the modulus of z minus I over I is less than 1. That was in fact, that's our common ratio, but this, since the modulus of I is equal to 1, this is the same as the open disk where z minus I in modulus is less than 1. Now here's what that looks like in the complex plane. Here's my real axis, here's my imaginary axis, here's I. And so we're looking at all points that are within 1 unit of I. So that's going to be this open disk. We know that on the boundary of the disk and outside the disk, my series diverges. Now, 1 over z, that's my function that I was expanding. It has a singularity precisely right here. So we can see that the power series expansion actually had a disk of convergence that was as large as it could be until it bumped into a singularity of the function. And this will be true in general, and this will lead us to the idea of Taylor series.